Hello everyone. Welcome to AFRICAI Journal Club. For those of you who don't know AFRICAI is the African Network for Artificial Intelligence in Biomedical Imaging, with the aim of promoting research in medical imaging within Africa and beyond. So, as part of our monthly meetings, we have the Journal Club, where it's a group discussion where you can come to discuss a high impact paper with the community. So feel free to sign up so that you can contribute with your discussion and your insights to the AFRICAI Journal Club that we host every month. And as part of promoting the Journal Club, we are giving funding for 2 awards of 150 euros for the best journal club, which are decided by the participants' votes as well as the evaluation by the educational chair. And today we welcome Ajibola in the second journal club. Ajibola is a final year PhD candidate in biomedical engineering at the University of Cape Town in South Africa. He holds a master's in microprocessor and control engineering from the University of Ibadan in Nigeria, and a Bachelor of Engineering in Electronics and Electrical Engineering from Usun State University in Nigeria. Ajibola was recognized as an outstanding reviewer for the last MICCAI in Morocco, and his paper, Spectromex, was accepted for an oral presentation at the conference with a spectacular rate of 2% for acceptance. So welcome, Ajibola, for our AFRICAI Journal Club.
Thank you.
And thank you for your voluntarily appearance.
Thank you.
Ajibola will be discussing today the Cascade SAM for sperm segmentation, which is the segment anything model, a viral model, and a trending model for medical imaging segmentation. Thank you.
Thank you very much for having me. I'll be sharing my screen shortly. Okay. Can everyone see my screen?
Yes.
Oh, thank you very much. Okay, so thank you everyone for joining today's Journal Club meeting. As Elias said, we'll be reviewing or evaluating, or not evaluating, we'll be examining this paper by Yishi et al., CS3, Cascade SAM for sperm segmentation. So my presentation will be broken in 2 parts. The first 30 minutes, I will be presenting some key insights that I got from the paper after reading the paper. I hope some of us were able to also read the paper. So in case if you have questions in the second section of my presentation, the next 30 minutes, you can address some of the questions that you might have from the paper, either from my presentation today or from your own personal reading of the paper. Then we can also discuss extra points, other additional points, such as how this approach can be adapted to other medical applications, for example, because this paper is basically, the domain for this paper is sperm cell segmentation. But how, if you're going to adapt this to another medical application, what will we do? What will we need to do? That sort of thing, right? So we can discuss that in the second section of today's meeting. And also what ideas, if you are going to improve on the paper, right? Either the methodology or some other aspect of the paper, the application, what can you, that's a good way to think going forward, like things you can build on top of, when you, after reading a paper, you ask yourself the question, if I want to improve this paper, what would I do? That sort of thing, right? So I'll start by just talking about the overarching clinical impacts of the paper. Most papers start with a global goal, like a global impact, right? And for the CS3 paper, the overarching clinical impact is automated sperm cell morphology analysis for the assessment of male fertility, right? So the morphology of sperm cells in microscopy images informs male fertility. So you can, a lot can be said about the fertility of a male based on the morphology of the sperm cells, right? So that's the overarching problem. But then the specific problem addressed in the paper. So typically, a lot of papers, you have a global or an overarching clinical problem, and it's a specific research gap that you are trying to address towards that goal, or the goal of solving the overarching problem, right? So in this the specific research gap addressed in this paper is the auto segmentation of sperm cells, right, towards morphology assessment, right? So before you assess the morphology of sperm cells, segmenting it in a unsupervised way, could be important, could be very useful, right? So existing segmentation methods, particularly for sperm cells, they struggle with instance segmentation of overlapping sperm cells, which may impact the effectiveness of morphology assessment, right? So we see that it's particularly details of a lot of the sperm cells overlap, right? So being able to segment each cell using instance segmentation, that is, identify each cell as a unique object in the image, right, is important for the global or the overarching problem or the overarching goal of assessment of male fertility. Right. So the paper presents CS3 as an unsupervised approach for effectively segmenting overlapping sperm cells. So we see that the problem is a very specific problem, and that's one of the hallmarks of a good paper, in that the problem you're trying to address must be very, very specific, right? So it's not just trying to solve the problem of segmenting sperm cells. We will see going forward that several other papers have attempted segmenting sperm cells, right? But here it's a very specific problem of the overlapping sperm cells, right? So this paper was accepted for MICCAI 2024, that was last year, and it falls under the category of clinical translation of existing method. That is, this method, CS3, uses an existing model. So there's an existing state-of-the-art model called SAM, segment entity model. We'll talk about that later, right? So this paper introduces a novel way of applying SAM for this specific task. So it's under clinical translation of existing method, right? So if the authors had developed a new model with a new architecture, then it would have fallen under methodological contribution, right? Okay, so we'll start by looking at some of the previous works or previous approach for sperm cell segmentation prior to CS3, right? So we see these authors introduced improved units. So they modified the traditional units for the goal of sperm cell segmentation, right? And this kind of paper would have fallen under the category of methodological contribution, because they're proposing a new model, right? Not just applying an existing one. And in their approach, they introduced a couple of new components to the traditional units. They introduce these blocks here in the skip connection, right? And then the novel thing that they added here was the special or a modified kind of convolution, right? Regular convolution, you apply your filter, your kernels in this form, right, where you are targeting neighborhood of pixels, right? But here they do diluted convolution, where you skip some neighbors, right? Uh, so that was the novelty of their approach, right? But looking at the results from improved units from this paper, I would say compared to the ground truth, their model was able to segment the heads of the sperm cells, right? So the model was adept at segmenting the heads of the sperm cells, but not the tail, right? So that's and also use supervised learning, which means you train the model using corresponding mass of the heads of the sperm cells, right? And we see that their model had less false negative compared to was able to identify more sperm cell heads compared to the original unit and a prior unit based method, right? Okay. So another approach prior to CS3 also performed segmentation of sperm cells. In this case, not just the head alone, but was able to perform full cell segmentation, right? But the limitation of this paper is that it did not address overlapping cells. So it's only for non-overlapping sperm cells, right? And it used the unmodified mask rCNN, right? So it's an existing method, right? Yeah. So it's another limitation. It's a limitation in the field, in the domain of sperm cell segmentation, right? And one other paper, bit more recent, considered overlapping cells, and it used an ensemble of models to address segmentation of sperm cells, particularly when you have overlaps. And it's a supervised learning approach, which means you provide masks for it. The model was able to do some limited segmentations, but we'd see that it's not able to delineate the tangled sperm cells, right? So in addition to addressing this, not being able to sufficiently address the sperm cell tail overlap, right? So prior approach relied on annotated images, right, to train models. So all the approach I mentioned earlier, they're all supervised learning approach, which means you need to painstakingly annotate all the images. You have to draw masks for every single sperm cells in the image and show how they overlap. You have to take cognizance of the overlap, right? Which is what makes it a difficult domain when it comes to machine learning, right? And that leads to scarcity of annotated sperm cell images, right? Because if you have a lot of overlap, you need to be a lot more careful when annotating, right? And that will reduce the number of annotated sperm cell images you can have, right? So, for example, you might not be able to have like 100,000 or two. It might not be easy to get 100,000, 200,000 annotated sperm cell images because of the difficulty in manually labeling them, right? So there's scarcity in sperm cell images, right? So that introduces a need for an unsupervised approach that accurately performs instant segmentation of overlapping and non-overlapping sperm cell images, particularly on unlabeled images without training. And this approach is typically called a zero-shot approach, right? So this is a domain that would significantly benefit from a zero-shot approach. And this paper, proposes CS3, which is a zero-shot approach that uses segment entity model. It's segment entity model. It's a state-of-the-art foundation model developed by MICCAI, right? About 2 years ago, 2023, right? So CS3 applied SAM, to perform the task of segmenting overlapping sperm cells, right? So that's the general picture of the paper. Right. So take a look at how SAM was trained, right? So SAM is a foundation model. It was trained on 11 million natural images, right? So not medical, natural images, and 1.1 billion segmentation masks, right? So SAM was trained with images of all kinds of objects in the natural world, right? Fruits, natural objects everywhere, right? And the mask, about 1.1 billion masks across all the images, right? All those masks were generated. A large portion of them were generated manually by expert annotators, right? And another portion of it was annotated using SAM itself. So there's an iterative method, but we won't go into that. But basically, 1.1 billion masks, we are trained. The model knows how to understood how to or predicted about 1.1 billion masks from 11 million images. So the model was trained to have zero-shot generalization on millions of natural objects. So it's expected that SAM has learned some general features that can help it to segment an object it has not seen before, right? Based on some semantics that it has learned from all kinds of natural objects, right? So SAM has a mode called everything mode, right? So in its everything mode, it can generate segmentations of all foreground objects in an image without any input prompt, right? So the training dataset of SAM did not include sperm cell microscopy images or any other medical image modalities, right? So the millions of images that SAM was trained on does not include medical images, right? By default. So the authors of CS3 performed some preliminary investigation to see if SAM on a zero-shot form can segment sperm images sperm cell images, right, without training, right? So Sam has not seen sperm cell images before, right? So if you feed in sperm cell images to Sam, can it segment individual sperm cells in the images, right, in the microscopy images, right? So that's a zero-shot approach, right? Zero-shot segmentation. So the authors of this paper did that preliminary just without modifying SAM, feeding the new images to SAM, and see if it can perform this segmentation of all the sperm cells in the images, right, in this everything mode. Right. So this preliminary investigation, it revealed three things. So this is one of the contributions of the paper, in that it's the first paper to give us the insights on how SAM, performs on this domain, right? Sperm cell imaging domain, right? So they found out that SAM prioritizes segmentation by color first and foremost. If you give it any image, it will try to segment the objects in the image based off of the color, the unique colors that they have. And then after segmenting by color, then it segments by geometric features, right? And then next, SAM prioritized easily segmentable regions like the heads. So the model segmented the heads first, right? And then if you take out the heads, right, the authors did that. They removed the heads from the images. Then Sam was forced to then target the tails. And then if you take out simple tails, then it will go for more complex tails, right? And then the final insight that they discovered was that for tails that were very, very thin and were difficult to segment, they discovered that if they apply some morphological operator on the image to thicken the lines, that those overlapping tails it will be easier for SAM to segment or to separate tails that overlap if you thicken the tails, that sort of thing. So, but all of these are like preliminary investigation, in the introduction of the paper, before they then implemented the insights from this. So they combined these insights from their preliminary investigation to develop CS3. So CS3 is based off of these three investigations, these three insights. So CS3 is proposed as an unsupervised approach for end-to-end segmentation of sperm cell images with overlapping tails, right? So you fill in the images, no further inputs from you. At the end of the day, you get individual segmented images as individual segmented sperm cell, regardless of whether there's overlap or not, right? So that's what CS3 is. So the stated contributions to the paper, it's the preliminary investigation, the development of CS3 as an unsupervised, although they use the word method. Generally in the MICCAI space, a proposed method is typically like a new architecture. Like SAM is a method, it's an architecture, it's a model, right? So, but CS3 is a pipeline, right? It just shows it's a approach that involves the use of an existing method, of an existing model, right? So it's more of an unsupervised algorithm or an approach or a pipeline, right? And then they show that CS3 outperforms existing method in segmentation or accuracy for the instances of overlapping sperm cell tails, right? So basically, the pipeline for CS3 in simple language is that they start by applying feeding the image to SAM, right, to segment all the heads. So it will automatically recognize all the heads, sperm heads in the images, right? And then the algorithm, the CS3, would save all the sperm heads and remove them from the image, leaving just the tails alone in the image, right? Then feed the image with just the tails to SAM again, right? That's why it's called CS3, cascaded SAM, right? Cascaded SAM for sperm cell segmentation, right? So they are applying SAM in a cascaded way, all right? So multiple rounds of applying SAM would gradually segment all the simple tails or the easily identifiable tails, the untangled tails, right? And then for every tail it recognizes, the algorithm will remove the tail and refeed the image again to SAM, until SAM is able to get to the more complex tails, the ones that are overlapping, right? So when there is no observed changes between, because it's like a recursive process, right? So there should be a way for the algorithm to know when to stop feeding the image to SAM, right? So for between every successive image, it checks to see if there was a change between before and the after, right? So when there is no successive changes, the algorithm CS3 applies morphological operation, line thickening, thickening the lines, right, with the assumption that there are probably some overlapping tails in the image, right? And then you repeat for some further runs after the morphological operation to see if SAM can untangle the the overlapping tails, right? And when there's still no change, then the iterative or the recursive process stops, right? And then, so now you have masks of fragmented cells all over the place, right? So, you've done this recursive process of picking of isolating and segmenting the heads and the various tailed fragments. Then the CS3 combines them, right? Takes all the fragments and use all kinds of different criteria to match the heads and the tails. So you have head fragments, tail fragments, match individual heads to individual tails to get complete sperm cells all over the image. Right. So your data set is composed of 2,000 unlabeled sperm cell images, and 240 of them are annotated, right? Yeah. So this is for model evaluation and benchmarking. Of course, although it's proposed as an unsupervised approach, you still need to know if the model is doing well, right? So which informs the use of 240 annotated images. So that way you can benchmark against existing methods that are supervised, use a supervised learning approach. Right, so just to show the application of the framework for CS3, right? So if you feed an unlabeled image to SAM model in its everything mode, right? And it's the first application, it would segment, it will recognize all the heads of the sperm cells, right? So it segments the head. Then the authors apply the algorithm applies some sort of color filter to extract or to remove the heads from the image, and then feed the image without the head to SAM again in a cascaded approach. And now SAM is now forced to recognize the next most significant geometric features in the image, right? Which are the simple tails, the single tails. So it identifies a single tail, then you separate, you take out the single tails. Now you're left with the overlapping tails, right? Then you apply a morphological operation, specifically line thickening, right? So it's a filter, just a simple filter. So you apply a filter, a kernel that thickens, that adds pixels to every line. It's almost like an edge detection sort of filter, but something similar to that. But here it is, you are modifying the image, right? And then you apply SAM again. This time around, SAM will be able to is able to recognize the overlapping tails and then segment them, right? Until there are no changes in the image again. Then you stop the process. The process stops, and then you do the match and splicing, right? So that's the algorithm. It's sort of like it's an algorithm that uses the SAM model as the central component, right? And applies the images to SAM in a cascaded way, right? So here we see that the mask, so it generates a mask for each object detected in the image. So here, like 6 heads, right? And then in the next set of runs, it identifies the tails, single tails. Next set of runs, then it identifies the complex tails, right? And then you do the match and splicing. So the algorithm sort of estimates so there's a criteria, although the authors they didn't give too much details on how they are able to, how the algorithm is able to tell that a mask has a tail and a mask has a head, right? But generally, it's not a difficult thing to do. There's some, criteria. There's some defining characteristics of what the tail is, right? So you can just a simple algorithm to analyze the blob, right? So each mask has some kind of a blob, right? So you can estimate that the structure of the mob, right? If the mask has this kind of structures, it's most likely a tail. If it has this kind of structure, it's most likely a head, right? And then they match based off of distance and the angle. So they use the distance and the angle of the masks to know what tail belongs to what head, right? And then they match them to form the individual sperm cells, right? Okay, so now I will talk a bit more about the SAM, because since the SAM model is the central player in this paper, right? In the approach, in the CS3 approach, right? And SAM's zero-shot ability is facilitated by the prompt table segmentation approach, right? So the approach was introduced by, or not introduced, but it's made popular by this paper, SAM, and it was written by Kilerov et al. In 2023. And for SAM, you feed in your image, not just your image. Now you feed in a prompt. We have three options, or there's a fourth option, but these are the three main options. So you either feed in a mask prompt, right? Or you feed in a point prompt or a box prompt. So a point prompt is you put a point. So you ask Sam that I want you to give me an object that is enclosed, or that an object in which, or for which the point belongs to, right? So basically, I give you a point. Around this point is an object, right? So give me the object that's around this point. So that's what a point. And if it's a box, so a box, but you give a box and say, okay, in this image, within this box, the contents of this box, give me the objects, right? The objects with the highest confidence that that belongs to this, that's within this box, right? So, and then instead of a box, you can use a mask instead. So for some, you almost always need to feed in an image and either of these prompts, right? Or a combination of the prompts. So that is what makes the zero shot. It's fast. It makes it easy for Sam to perform zero shot segmentation, right? Because there are all kinds of things all kinds of objects that can exist in an image. But once you give it a point or a box or a mask, you constrain the space of the number of possible objects that can be segmented in an image, right? So it hates the zero shot ability of SAM. And SAM gives you 3 sets of masks, right? And for each mask, it gives you an IOU score, like a confidence score of how well it thinks that mask matches the object that it thinks it identifies in the image, right? So this is the schematic of SAM. So SAM there's an image encoder, right? So when you feed in your image, there's an image encoder that encodes the image into a dense embedding. And on the other side, where you have the prompt inputs, right? So you either feed in the mask prompt, a point prompt, a box prompt. There's an option for a text prompt, but it wasn't. It was proposed, but it wasn't implemented in SAM. I think it's still experimental, and it comes from another model called Clip, right? So basically, you put in a Clip model here. So Clip would generate text embeddings that are image aware, that sort of thing. So such that you just put in text and say segment every sperm cell in this image as a text, right? And that would be the input rather than feeding in points or box. You just feed in text, right? But it's experimental, and the result that they showed in the paper, that's in the original SAM paper for the text prompt, we are still at some wasn't as good as the other prompts, right? So which is why in the deployed version, I think these 3 prompts are the main prompts being used, right? So whichever prompt you use, if you use a point prompt, right, you have it's X and Y coordinates, and this is a flag to tell Sam whether this point is a foreground or a background. It's just a single flag, right? Right. So if you are telling that the object that I want you to segment is a foreground object or a background object, it's a flag, right? So X and Y coordinates, and then if it's a box prompt, you give it X1, Y1, that's this edge, and X2, Y2, that's this edge, right? So there's a prompt encoder that encodes the points or the box or the text, right? And if it's a mask you're feeding it, it's downsampled using some convolution layers and combined with the embeddings from the image encoder. And then most of the work is done by the mask decoder. The mask decoder is what does the work that combines the embeddings from your prompts and the image, and then the output is mask. Three options. It gives you 3 options. There's a 4th option. So that 4th option is what it considers the most confident one, right? So, but these 3 options are, so you have options. So SAM gives you 2 options. Do you want 3 masks or a single mask? Do you want 3 masks, 3 options that is ambiguity aware, which means that it can give you a subset of what it thinks you'll be. For example, if I put a point here, right? It's either I want you to segment just you. So that's why it's ambiguity aware. Right? So it's either you want Sam to give you this ambiguity aware options, or it gives you a single, just one mask that says, okay, this is my most confident mask based on the points or the box prompt that you gave me, that sort of thing. right? So feeding the sperm cell images in CS3 to SAM, right, which is what the authors did without the prompts, which is what the CS3 proposes, that a way to feed images to SAM, and it gives you mask without having to prompt it. Because if you need to prompt it, then it's no longer an unsupervised approach, right? It requires manual input. So say put point here or put box here, right? So the authors propose a way to, not a way to do it, but they use this approach, and this is what is called the everything mode of SAM. So in SAM, there's a way to use SAM in this way without putting prompts, right? And it's called the everything mode of SAM, right? So the way SAM does this in the everything mode is that internally it generates a 32 by 32 grid of points, right? So if you feed an image, it generates 1,024 points, right? And overlays it on the image, right? Then it feeds each of these points to its prompt encoder. So the prompt encoder is still working on the inside, right? Just that you're not the one feeding the manual points, right? So for each of the 1024 or 1024 point prompts, right, SAM predicts a mask and a corresponding IOU confidence score, right? So you feed in the image, it generates 1,000 points internally. Then for each point, it generates 1,024 masks and corresponding IOU scores, right? Then SAM filters the masks that have very low IOU scores. For example, the mask that comes from this point now, it's not going to be a very coherent mask, right? Because there's no local object here, right? So the IOU score will probably be low. So it filters those ones out. But the mask that comes from this point, for example, will probably have a higher IOU score. So it filters that, and maybe you get like you get 6 masks, right? Corresponding to the 6 heads, right? Which was why when the authors applied this sperm cell image to SAM, it only segmented the head, because the mask that comes from trying to segment the tail will probably have a very low IOU score, right? Because the mask will probably very like a very narrow mask, like the shape of the mask, right? So SAM is comparing whatever mask it gets from all the masks that's been trained on, right? So there are probably not too many images that have this shape, this sort of narrow shape, which is why SAM will not be too confident about that shape, right? But then there are probably many objects in the natural world that has this kind of oval shape, like fruit. So which is why SAM would have a high confidence score for this, for mask of just the head alone, right? So it will filter out all of the rest, all of the other masks, and give you just 6 masks, for example, right? So which was why the authors then this informed the next step in the algorithm, which was to remove the heads. If you remove all the heads in the image, right, and feed the image back to SAM again with just the tail, now SAM would have to generate mask for the tails and not filter them out, because there's a threshold, right? So if the highest IOU score, predicted IOU score, is for a tail, it will have no choice but to retain it rather than discard it, right? So the next step, what I've done now is like go into a deep dive into some of the blocks of the model of SAM, right? So the encoder part of SAM, right? The encoder part is based off of another approach, right? Which is the mask autoencoder approach, right? So the way the mask autoencoder works is that they build an encoder and a decoder. Then you take your input, and remember that SAM was trained on 11 million natural images, right? The encoder and decoder, they are vision transformer based models. If you mask about 75%, right? Remove mask 75% of the image, leave only 25% of the image, right? And you encode it into an embedded space. This embedded space is dense. It's smaller than if you had used all the full images. Then you would ensure that you keep track of the position in the image, right? So that you don't lose the position of the patches, right? And then you use a decoder to try and reconstruct the miss. So this part that is missing, right? These are the missing parts. The decoder is able to construct or predict the missing part just from the information, like the 25% of the information that is given to the encoder, right? So the whole purpose of this is that you want an embedding space that is compressed, that is dense, but also is generalizable. So which means that whatever the information in this embedded space contains some general information, generalized information, that can generalize to and give you zero shots performance for other tasks, other objects, right? You don't want to overfit. So it's an approach that makes your model more generalizable, which is why this approach was used for this foundation model, right? So the weights of this encoder after training it, or rather after reconstructing about 11 million images using this approach, right? If you freeze the weight such that you no longer want the weight of the encoder to change, right? So this encoder becomes a very good generator of image embeddings, generalizable or generalized image embeddings, right? So if you feed in an image, it gives you a dense image embedding that is in a space that is more generalizable than if you had used the full image, right? Then you discard the decoder, you feed just the encoder, you bring the encoder here into SAM. So the encoder of SAM was gotten from a masked onto encoder, right? Okay, so just quickly talk about the other blocks in the model, the SAM model, right? So you start by feeding an image to the image encoder, right? And we've explained that the image encoder is from the masked autoencoder, right? And that will generate embeddings. So the embeddings they are dense embeddings, but they are in a feature space that has more generalizability than if you had used the full image, right? And then the mask prompt, if you have a mask prompt, right, it's fed to this convolution layer that downsamples whatever mask you have to match this shape, right? A shape of the image embeddings, right? And then here, you have a block here where you sum up, you do an element-wise addition of your embeddings and your mask embeddings and your image embeddings, right? So you had them element-wise, you get the same shape, right? And then you can flatten the embeddings, right, to give you this shape, right? So now looking at the prompt encoder side of things, right, a single point, you feed your single point to a prompt encoder. Inside there's a position, you perform position encoding. So you encode your X and Y coordinates to a 256 dimension token, right? And you do that for your box prompt too, right? And so you have this embedding for your point, this embedding for your box. Now, these embeddings here, they are statically initialized. They are blank, or when I say blank, they are defaults for now. Eventually, these embeddings will become the mask, the predicted mask. But initially, at the very beginning, they are initialized, randomly initialized, if you can put it that way, right? And then this last one, last embedding is for the predicted IOUs. So the predicted IOUs will be trained here, and the masks are trained here, right? So this is the mask decoder, right? So we have the prompt encoder here, the convolution layer here, the mask encoder here. So most of the work is done here in the decoder, right? So the decoder has an inner block and an outer block. So this is the inner block that's repeated twice, right? So the first thing that occurs in the decoder is self-attention, right? So the attention, of course, some of us might be aware, might be familiar with attention. It follows it's just about you applying the formula or the equation for attention, right? So here the query, the key, and the value all comes from the same embedding, right? And the point of this is to make each token aware of the next token, right? So the output here is going to be the same shape as the input, but this prompt embeddings are context aware. So your point prompt is aware of what your box prompt looks like. That's aware of what's the masks and then also the IOU. So everything is aware of everything. That's what the self-attention does there, right? And then next we do cross attention. So the image is on this side, right? So you feed your images as the key and also the value, while the query matrix comes from your prompt embeddings, right? So the output of this, is image aware prompt embedding. So now your prompt embeddings is aware of what the image looks like. right? Same thing to all the mask, or what will eventually become the mask, right? So the mask is now aware of what the image is, right? Then you feed this to your multi-layer perceptron. It's just a neural network, feed-forward neural network, which would bring in some non-linearities, and also it's where most of the learning occurs. So it sort of learns what is important, right, from this embedding space. And also, it's also like a memory too. So it also stores, like it learns and it learns and it memorizes the important things from the embedding space, right? So now we also do attention on the other side of things, right? So we perform cross attention again. This time around, the query comes from the image embeddings, and then the key and value come from your prompt embeddings, right? And then you get your prompt-aware image embeddings. So these image embeddings they're not aware of the prompt, and then this one is aware. It understands what the prompt is, right? Right. So the output of the inner block of your mask encoder is the prompt-aware image embeddings and image-aware prompt embeddings, right? So the final layer of the model, right, it takes the prompt-aware image embeddings, reshapes them, right, and upscales them such that now we have the spatial dimension is greater. So 256 by 256 model, while the number of channels is reduced, right? So it rescales them. And then we discard the prompts and the point prompt and the box prompt embeddings, right? We don't need them again, right? What we need now is the mask. So each of these token is for a single mask. So this is for the first mask, right? You feed it through an MLP, feed forward neural network, second and third, and then the fourth, right? And then the output of that, it forms this 4x32. So we scale down the dimension of each token from 256 to 32, and then we have four of them, one for each mask, right? Now we take a product of each of this embedding space with the image embedding, right? So if you take a product of that, if you look at the dimensions, this dimension will match this dimension. We do it for each of the embeddings or the tokens. And then the output will just be a single a vector of this shape. If you reshape it, it forms a 256 by 256 probability map. If you threshold that map, you get a mask. So that's how you get your first mask, right? You repeat this process for the others, you get second and third, and then the fourth or the final mask, right? So basically, this is how SAM was trained, right? This is the architecture for SAM, right? And now the final embedding here is fed to a feed-forward network with 4 neurons in the output, right? So each of those neurons is to predict an IOU score, right? And that tells you how confident it is for each mask. So the IOU score for mask 1 is this, mask 2, mask 3, and mask 4, right? So if you want SAM to give you ambiguity-aware options, it will give it would only output just these three, the first three. But if you want it to give you confident mask, the most confident mask, the mask that is the most sure of, then to give you only mask 4, just the last one, right? So in the training, when Meta was training the model, then they introduced a loss function, right? They feed in a ground truth mask, and then to compare the mask with the ground truth mask, and then it will compute loss. They use focal loss and dice loss, right? And then it back propagates through the model to update the model parameters. But for CS3, SAM was used in the everything mode, right? So in the everything mode, no training occurs again, right? So it's a pre-trained model. All the weights are frozen, right? So it's used in inference mode, right? So you feed in the model, it gives you the mask, but there's no back propagation, right? Okay, so finally, we just look at the results, right, of applying CS3 with this approach on the images, right? And CS3 outperformed SAM. So this is SAM without all of the cascading approach and application of the line thickening morphology. So SAM 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 without any additional image processing, right, gave this approach, gave this mean IOU and mean dice score, right? So we see that CS3 did well for the task for the specific domain. And then for the qualitative results, these are the images or some images, raw images, and then the ground truth, which means annotated version, so annotated by human experts. And then CS3 was able to identify, was able to segment the cells, and where there are overlaps, so that it's able to take care of simple overlap, but it still struggles with complex overlap. So we see here there are about maybe 3 or 4 overlapping tails. Even the human annotator, the expert struggling with annotating where there's overlap, right? So we see that it's not perfect yet. There's room for improvement. And we see that there are also very, very thin tails, tail fragments that even the human annotator also ignored. Also, some also seem to ignore some of them. For example, he wasn't able to, he didn't pick this tail, right? You only pick a section of a tail, right? So there's room for improvement, but it's definitely seems to outperform some of the other state-of-the-art methods, right? So in conclusion, the paper revealed challenges of a zero-shot approach, that's using SAM, for example, for the specific domain of sperm cells segmentation. And CS3 achieves better segmentation of overlapping sperm cell tails compared to state-of-the-art models that use supervised learning. And the authors state that their future work will focus on automated sperm morphological classification method based on the segmentation results from CS3. So basically, after segmenting the individual cells, what analysis can you do to differentiate one type of sperm cell from the other? Are there deformities? Is this a healthy sperm cell? All these kind of things, right? So layering that on top of this segmentation is a future work of the authors, at least according to the paper. Right, so just one or two limitations in the paper. The approach seems to struggle to disentangle more complex overlaps of tails, right, as shown in the earlier results. And also the approach seems to assume that all sperm cells in the image are simple single tail cells, right? It does not address the presence of sperm cells with non-typical features such as multiple tails attached to a single head, right? And that actually it occurs, right? So this is another paper that details all the various kind of deformities that can occur. So you can have some sperm cells that have two tails, for example, some that have some kind of weird abnormalities, So this paper does not, CS3 does not address whether how well SAM can do on this kind of approach. So these are, areas of future research, also things we can discuss shortly now. So thank you for your attention. If you have any questions, we can discuss them.
Thanks, Ajibola, for this nice presentation. Thanks a lot.
Yeah.
It was very clear, honestly, and the way that you discussed the segment anything model in details, I couldn't see this in the paper for sure.
Yeah.
It's very nice to have this introduction for it. So how do you think this paper can be applied to other modalities? For example, you mentioned that this was definitely done for the overlapping stuff like the sperm,
Yes.
but you can have this in cell segmentation. You can have this also in histopathology. There is a lot of overlapping structures. Do you think
Exactly.
the same method can be applied given that I believe it's very domain specific, or what do you think?
Yes, you're right. It can be applied in other fields too, right? In other applications. So the most important thing is just to identify the peculiarities of SAM, especially if you're using SAM. Right? So for example, here they discover that when you apply SAM to their specific domain, right? SAM prioritizes some kind of structures. So if you feed in another type of image, another type of microscopic image of overlapping cells, right? It would prioritize some kind of cells over some other kind of cells, right? Now that's where your ingenuity there comes into play. Like, okay, what can I do to make SAM? That's if you're going to use SAM in a zero-shot approach, right? To make SAM also not forget to identify those other missing pieces. So in this case, they did the line thickening, right? So when they discover that after the edge, it prioritizes the edge, forgets that it doesn't bother about the tail, right? So they remove the head, right? And so you can do that for another application. But then if it's still struggling to identify some things that you're interested in, then you can probably do something like some kind of image processing. Here they use line thickening. There are all kinds of image processing filters that you can apply to, so that's where the experimentation comes. Like, what can I do to my images to make SAM identify what I'm interested in, And that thing you can do is to do what is called few shot learning. So few shot learning is you take some images and some mask and you fine tune. So because SAM has not seen this kind of images before, right? So if you feed like maybe 100, if you take 100 annotated images and tell SAM that, okay, for this is how this is what I want you to segment, right? You provide mask and you provide 100 images, right? So it would add that knowledge to its existing knowledge, right? And then, able to, yeah, exactly. So that's few shot learning, exactly. So you can add few shot learning to zero. So instead of zero shot learning, where, Sam does not see anything that has to do with this new domain, you just give some few examples. That's few shot learning. Yeah.
And have this paper explored any ablation regarding this or not?
No, I don't think they did an ablation in this paper. Okay, well, they did. For this paper, they showed us the IOU score of SAM without their. So ablation, basically what happens by default, and what happens after they. So they do it just a SAM and CS3. Yeah. So SAM and CS3. SAM is the default. Their own SAM without their input, their image processing inputs, right? And then CS3 is SAM plus their cascaded approach and the image processing thing.
That's super interesting. Yeah. Thank you a lot. That definitely answered my question. Thanks a lot for the insights.
You're welcome. You're welcome. Yeah. So I don't know if there are other questions.
But I was asking also, like, for the results, like they were able to achieve over dice like 80%. Is this task very critical when it comes from the clinical aspects? Like, is this sperm segmentation, like the clinical impact of such task? How clinically impactful? Like, do they need actually like 80%, 90, 100? How much is acceptable, or
Yeah, so yeah, that's a good question, right? So from I think in the domain, segmenting the sperm cells probably is not where the impact is, right? Like the impact is, they also mentioned that in their limitation. The impact comes from being able to identify abnormal sperm cells, right? So a healthy sperm cell would probably look maybe something like this or something like this, right? So if all of this, they are all abnormal, right? So an healthy sperm cell would have this white section is where the information is, right? The whole thing would be white instead of black. So it would be it will look something like this, but the white section inside, I've forgotten what it's called now. It's where the payload is, right? So being able to identify this. So the authors say that after segmenting, identifying, or being able to separate individual cells, then they do analysis that in the feature study on, is this cell viable or not, right? Then you estimate how many deformed cells come from the patients compared to the healthy ones, that sort of thing, right? So I guess that's where you begin to get the impact, right? Which is why there was an overall or overarching impact, and there's a specific research gap. So the research problem addressed in this paper is towards the overall goal, which is being able to identify deformed or non-typical cell unhealthy cells. Right? So, but the 80% on its own, the clinical impact is not huge, if I can put it that way. Just being able to segment individual cells, right? But then if your end goal is to be able to identify or classify, which cells are healthy, which ones are not healthy, then now you are it's now becoming more now you're talking more about the impact, clinically useful impact. But just being able to segment it on its own does not have much clinical impact. But then yeah, and the author discussed that they will do that in the future, or they plan to do that in the future study.
Yeah, and I think, as you mentioned, it makes complete sense in the sperm selection
Exactly.
this way, because if any procedures like the IVF or any procedure that requires sperm to the eggs, make complete sense that it needs to identify or segment the sperms first in this direction. Thank you a lot. Is there any questions from Gustav or Ayomadi or people attending or confidence? Do you have any questions?
Hi, Ajibola. Thank you so much for the wonderful presentation. Nice to meet you again. It's a great one, to be honest. I love the flow of your presentation and how easy you made everyone understand the concept around this SAM model. My question would be like, based on personal experiences and some of other researchers, how is SAM usable for researchers within the LMIC, considering the computational demand, are there ways to limit the resource demand for this particular model and make it more lighter or more trainable enough for researchers within the LMICs where access to GPU and GPU times are limited?
Thank you very much for that question. For that, that's a perfect question. From the point of view that that's actually what SAM is going for, right? SAM in its everything mode, in its inference mode, right? So we are not training it. That's one. And two, if you go to the SAM website right now, right, and you upload an image, right, from your browser, you can perform segmentation, in seconds. And the way it does that is that most of the work is done in the image, from the image side of things, right? The image encoder, it's why they use the mask encoder, right? The mask autoencoder. It's lighter, one. Two, it's frozen, right? It's even when you are doing the fine-tuning, you don't touch the weights of the image encoder don't change, right? So when you fill in an image, it generates the prompts, the embeddings, right? And it caches that, right? So if you then begin to put in different prompts, it doesn't do this process again, right? So it does this once for every image. It does this once, gives you, because the embeddings don't change. It's you have this. It's like an embedding generator, and that is it's the heaviest part of the model. You see that every other part of the model, it just works with like points and how to transform the embeddings. And the embeddings are already dense. They are more dense than your image. Right? So this is the heaviest part of the model, and SAM was Meta AI. They had a goal in mind of LMICs, and not just LMICs. This version. There's something called the SAM2. SAM2 actually works on video now, right? So that's multiple frames, right? So their goal was to go towards SAM2, and SAM2 is used by robots, right, for their vision task of recognizing what is a laptop, what is object in the scene. So they needed something very light, something that can work even without GPU, right? So remember in CS3, they did not train the model again. They used SAM in inference mode all through. They only just added image processing on top. And image processing, you don't need GPU, right? So if applying SAM in everything mode does not need GPU, right? And your image processing on top of it doesn't need GPU, then the whole process doesn't need GPU, right? And that's what makes in CS3 and even SAM like wonderful for LMICs, right? So you don't need to fine-tune if you don't have the GPU. You don't need to, even if you want to fine-tune, you can decide not to even in fact, you don't need to fine-tune the image encoder. If you want to fine-tune to a specific task, you can freeze this. You only need to just fine-tune the lightweight. Remember, they also put lightweight mask decoder. So the mask decoder is very lightweight, right? This is heavy. If fine-tune this would take a lot of GPUs, but fine-tuning lightweight, that's if you even need fine-tuning at all, right? So SAM was built with the goal of LMICs, or no, not LMICs, with the goal of vision tasks like robotics, like video streaming, like that kind of object detection or segmentation in video streams, right? But that also helps LMICs where you don't have GPUs, right? So I don't know if that addresses your question.
Yes, it does. Thank you so much.
Yeah, you're welcome.
Thank you.
Thank you a lot, Ajibola, for this. And yeah,